in arbitrary coordinates, in arbitrary coordinates, and in GR, straight lines in curved spacetime. This led us to the next topic, which is on the geodesic equation. But before I talk about the geodesic equation, I just wanted to say a few words about the inverse metric. In particular, I wanted to talk about the notation that we're going to use, right? Because the inverse metric is going to appear in the next few slides. Okay. Typically, if you have a metric, right, then you are going to denote the metric without any index. You are going to use an indexless letter, for example, A, to denote this matrix. And you are going to denote the elements of the matrix with an index letter. For example, Aij, where I denotes the row and J denotes the column, right? In this way, so that whenever we write I2, A12, this refers to the element in the first row, in the second column, right? Which in this case is the number 3. Okay. Now, from this, if you notice, today when I introduce the metric, right, I write it in this way. So this is actually a bit of an abuse of notation. Okay, just because here it is as if I am writing that the element is equal to the whole metric, which doesn't really make sense. Okay, instead, what I mean really when I write this, what I mean really is that Jij and Gij are elements of a matrix representation of the metric tensor. This one. That's so this is what I mean. This is what I mean. This is what I want to say actually. But this kind of annotation is common, so I'm just gonna keep on using it. Okay. Now with this notation in mind, with this abuse of annotation in mind, I'm going to introduce the inverse metric. So given a metric of this form, we can then define an inverse metric. I'm going to denote with g to the power of -1, all right? Such that if we take a product between the inverse metric and the metric, we are going to get the identity matrix. If we now consider element by element, we can write that the element of this equation, the element of the first equation, is going to satisfy this equation, this first equation. Whereas the element of the second equation is going to satisfy the second equation. Okay, where this delta ij is the chronicle delta. Where you might want to recall that the chronicle delta is, by definition, is equal to 1 when I equals to j, and it is equal to 0 when I is not equal to j. Okay. When I is not equal to j. Okay, now one thing that I wanted to notice that we write the inverse metric using upper indices. Using upper indices. Yeah. The real reason is actually because it is a different type of tensor. But then because we do not really focus on tensors in this workshop, I'm just going to note over here, but I'm not going to comment any further. All right. But we also need to use upper indices in order for us to use the Einstein summation convention. Okay. Otherwise we cannot suppress this summation. Okay. So let me just recall. In the Einstein summation convention, we are just going to write this as j and jk g to the -1 ai equals to ij, right? Where because we have an upper and lower indices, second. Right, because we have an upper and lower indices, k over here, then this implies that we should sum over k. We should put a sum over k. We cannot do this if both if k appears in the as the lower indices in both in both in both the metric and also the inverse metric. We need an upper and lower indices. Okay, now because we always because the inverse metric will always have upper indices, usually you would find that literatures would just further suppress this -1. Alright, so instead of writing it in this way for the inverse metric, we're just going to write the inverse metric as GIK, for example. We're not going to use this -1 superscript. Okay, with this being said, then now only I can go on to talk about the geodesics. So I'm just going to introduce to you the geodesic equation first, and then later I will motivate why it takes this form. Okay, so this is the geodesic equation. Okay, so it is a second order equation, second order derivative, second order differential equation this way. Right? For each mu equals to 1, 2, 3, etc., etc., where n indicates the dimension of the space, or in the case of space-time, the dimension of the space-time. Right? Where you should also note that here I'm writing it in such a way that we start the sum from 1. Typically in GR, we are going to denote the first index with a 0. So if we have a 4-dimensional spacetime, and this is going to be a sum from rho equals to 0 all the way to rho equals to 3. So 0, 1, 2, 3, going to get 4-dimensional spacetime. Yeah. So but for space, we would typically start with 1. So this is the geodesic equation, and this symbol over here, this gamma, mu, rho, and sigma, is what is known as the Christoffel connection or Christoffel symbol. Where in GR, it's going to take this complicated form. Okay, this complicated form. So you can already see how many summation appears, right? This is why we would prefer to use the Einstein summation convention. So otherwise, you're gonna have to keep on writing this summation symbol. Okay, now what is the geodesic equation? Geodesic equation, as the name suggests, it is an equation for geodesics. And what is a geodesic? Geodesic can be defined in two ways. Right? It is either a curve or path that is straight in that particular space or space-time, or the shortest path between any 2 points in the system in the space. Right? So these are two ways in which you can define geodesic. Right? But then I must also say that both of these definitions do not necessarily imply each other. Actually, if you go deeper, then this definition, they do not actually imply each other. So let me just make a note over here, although I'm not going to comment much. So they do not necessarily imply each other. Okay. Okay, just another note so that you know. but they are equivalent to each other only through in what is known as motion-free space. Right? So something that you might want to look up further if you want to know more. Okay, so I'm not going to comment much about this. Okay, but anyway, you should just know that. So over here we have two definitions. We have two definitions in the space where we are dealing with GR. This is usually true. This is true. In GR, this is true. So in GR, you can use either definition. You get the same thing. So definition that we're going to use is the first definition. We're going to use this geodesic equation to describe paths that are straight in that space. All right, so I have introduced this geodesic equation. In GR, this geodesic equation is going to describe straight lines in a general curved spacetime. Right? In a general curved spacetime. Okay, this one here. So in GR, so the geodesic equation, it defines the path that an object will take in the absence of any external force. Right? One thing that you have to take note of here is that gravity is no longer viewed as a force. In GR, gravity is no longer a force. Okay? So this term, in absence of external force, means that the object is only being affected by gravity. So that is what is meant by in absence of any external force in GR. Gravity is no longer considered as an external force. Okay, so now I've said just now that the geodesic equation is used to define straight lines in curved spacetime. But actually, the geodesic equation is also the equation that describes straight lines in flat space, but in arbitrary coordinates. Okay, so the geodesic equation describes a straight line not only in curved space or space-time, but also in flat space, but in arbitrary coordinates. For example, in the polar coordinates or in some other weird coordinate that you might think of. Okay. So this workshop, we are not going to derive the geodesic equation in the context of curved spacetime. Instead, I'm going to just motivate you. I'm just going to motivate why it takes the form that it does by using flat space, but in arbitrary coordinates, in arbitrary curvilinear coordinate. How can we see that? If you recall, if in ordinary flat Euclidean space, right? In the Cartesian coordinates, we have that the metric is just a constant. Right? It's just 1 in the diagonals and 0 everywhere else. And in particular, because of that, if you notice one thing, this Christopher symbol, it consists of derivatives of the metric. It consists of derivatives of the metric. Therefore, in the Cartesian coordinates, the Christopher symbol is just 0. It will just be 0. So, because of this, the geodesic equation is going to just reduce. So this part is going to be 0. So we are left only with this part. We are left only with this part. And we are reduced to only this equation. which is none other than equation for straight lines, for parameterized straight lines in flat space. Okay. So, all right. So now I'm going to motivate the origin of the Christoffel symbol using examples in flat space. So we consider the motion of a ball on a tabletop. Then in the Cartesian coordinate, the motion of the ball is going to be given by a curve, right? By a parameterized curve, but curve and that is parameterized by the time, right? By our ordinary time. Right? So we have that. So this is the Cartesian coordinates, and right, so this is the curve, right? And at any time, we can describe the if this is the position at time t, and the coordinate is going to be x at t and y at t. Okay, that's wrong. Sorry, something is wrong. Okay, so given this curve, we can then define the velocity and the acceleration components in this way. In this way, straightforward way, we take the first derivative to get the velocity, and we take the second derivative of the position to get the acceleration component in the x direction. So this is familiar. In the absence of any external force, okay, then okay, so here we are using the framework of Newtonian physics. Okay? So in the absence of any external force, then we know that the ball is going to follow a trajectory that is defined by vanishing acceleration. Okay? So we have, from this, we are led to this condition, that is the velocity is constant. Both components of the velocity is going to be constant, right? Which I'm going to denote with Vx naught and Vy naught. Okay? From which we can and further integrate to get that the solution is going to be of this form. Okay, which is none other than just a straight line, right? Where this one is going to be the initial position, and this v are going to be the initial velocity. Okay, which are the velocity and the position at time equals to 0. Okay, now a question: how about if we use the polar coordinate instead of using the Cartesian coordinate? What if we use the plane polar coordinates? Okay, then if we follow what we did in the Cartesian coordinates naively, then we would say that the position is going to be given by these coordinates, and the velocity is going to be given by the first derivative, and the acceleration is going to be given by the second derivative. For example, right? If we just do it, maybe we can just apply the equation that we just looked at just now. Then, if straight lines are given by these conditions, then using the same idea, that is, straight lines are given by vanishing acceleration in this way, then we are going to be led to this solution. We are going to be led to these solutions where the V naughts and the R naught, theta naught would indicate the initial velocity and the initial position. Okay. However, suppose we consider the case where the initial position is at r equals to 1 and theta equals to 0. Okay. If I draw it here, so this is y, this is x, and this is constant r. This is constant angle, constant theta. This is constant theta. The green one is constant r. So suppose that we consider a case where we have that the initial position is somewhere here, right? And the velocity is only in the north direction. So this one is equals to, so this one is equal to 1. Okay, suppose that the velocity in the theta component is equals to 1, then you are going to be led to this solution. We're going to be led to this solution where r remains at 1 and theta increases with time. This, if you refer back to the coordinates, this means that the path that is going to be followed is going to be a path of constant r. Right? Path of constant r equals to 1. And this is a circle. Right? This is a circle. This is not a straight line. Okay? This is not a straight line. So what went wrong over here? Wrong is because we are using the wrong sets of equations in order to describe straight lines. Okay? If you recall carefully, then the condition for the absence of force, that is Newton's second law, where F equals to 0, is not. It is not a scalar equation. It is an equation that involves. Vectors. In particular, we have this equation. Take note that here, so this equality, we have the derivative of the vector velocity with respect to time, that is equals to 0. Not just the component, not just the derivative of the component equals to 0. So while this condition does translate to the components of the acceleration in the r and theta direction to be equals to 0, it doesn't actually follow from this condition. It doesn't follow this equation. We don't get this equation from a equals to 0. Instead, why is that? The reason is because of the following. So in the Cartesian coordinate, so again, we're going to use a Cartesian coordinate first. X1. Suppose that we have a path something like this. Something like this. And at each point we have the velocity of the path, right? This is t at t2, maybe this is velocity at t1, for example. Right? One implicit thing is that using the Cartesian coordinates, we define the basis vectors, the unit vectors at each point in a similar pattern. Right? Like for example, at this point, we have I in this direction and J in this direction. At this point, we have J hat here, I hat here. And at this point, we have I hat here and then J hat here. And so on and so forth. Every point, this is what the unit vectors look like. And hence, if we take the derivative of the vector, if we take the derivative of the tangent vector v, when we first write where we first write it in the component form, where here I'm using Ex, where this Ex correspond to our I hat, right? And EY correspond to our J hat. So I'm using a slightly different notation over there. Notice that when we take the derivative and when we apply the chain rule, and when we apply the product rule, we need to take into account the rate of change of the basis vector of the unit vectors as well. But throughout our trajectory, throughout our so this one I'm just showing a curve space, a curve line. But if we consider a straight line, well, we can even consider this curve line as well. Notice that as you travel along this curve, right, the basis vector doesn't change. The Cartesian coordinates, the basis vector doesn't change. So the Cartesian coordinates, we have that this is equal to 0, this is equal to 0. So you are left only with this term and also this term. So that when we impose the condition of no, no external force, that is, when we set this one equals to 0, this would imply each of this component equals to 0. So dvx dt equals to 0, and this is also equals to 0. Vy is also equal to 0. Okay. However, now what if we have the polar coordinates? Let me just draw it. So we have, again, using this is our main reference, and now take note of this. So I'm just going to draw next using just still. So this is the line of constant theta. This is lines of constant theta, and this is lines of constant r. About the basis vectors at each point. The basis vectors at each point, if you look at this one, at this point, for example, the unit vector in the r direction is in this way. This is our r hat. At this point, this is our r hat. At this next point, this is our r hat. And here, this is our r hat. Whereas our theta hat, that is the basis vector at each point in the direction of increasing theta. Here, here, here. But you can see that throughout the space, the basis vector changes. The basis vector changes. So when you consider a line, so when you consider any curve, all right, you need to take into account the fact that the basis vector changes as well. Right? The basis vector changes as well, and in particular, in general, so instead of having that the rate of change of the basis vector equals to 0, again, let me just make a note that here, this one is referring to r hat, and this is referring to theta hat. Right. So along any curve, the rate of change of the unit vectors is no longer 0. right? Instead, in general, suppose for example, if you go the rate of, but in general, you can write. So in general, we have that, for example, the rate of change of one in general, it is going to be proportional to some combination of the basis vectors at that point. Okay, so F R R theta, for example, and then this is G R theta, and E E the theta is going to be G R R theta theta. Um, sorry, F theta, and then this is G theta R theta. Okay. So why is this? Because you can think of it in this way, right? So suppose that you are traveling just along this point, right? So at your initial position, the direction of R is going to be in this direction. But at the next infinitesimally close point, the direction of R is going to be slightly in this direction, slightly, right? Which means that which means that the change, which means that the basis vector as you move along this line is going to be changed by this amount. It's going to be changing in this by this amount. So this the rate of change of R is going to be given by this vector over here, right? Which we can, of course, we can resolve this vector in terms of the basis vectors again, because a vector can always be resolved in terms of the unit vector. So in general, the rate of change is going to be again proportional to some superposition of the unit vectors in this way. Okay, I've written ER. Sorry. All right. Okay, now it is from this observation that we can obtain the geodesic equation. So I did not type it out because it's going to be quite lengthy. So I'm going to derive it now. So let's begin. So here I'm using an arbitrary coordinate system. Okay. Then what we can do is the following. So if you consider rate of change of v with respect to time, where we first write the vector v in terms of some basis, which I'm going to use this notation. Where this e over here is the basis vector in the ith direction. This is the basis vector in the ith direction. All right. Now, one thing that I wanted to note is that here I am using a general basis vector, which is not necessarily a unit vector. All right. So I choose it, E such that Vi is going to be equal to Exi dt. We can do this. All right, we can do this. So is this okay? Now with this, we can then proceed to do the derivative. First, we take out the summation outside. Thank you. Take the summation outside. Then we apply product rule to this product of VI and also EI. EI and also EI. So if we do that, we are going to get first dVI dt, and then dI, right? And then plus dI, and then the rate of change of the basis vector. So over here, so the first term, we're not going to do anything. Just to leave it like that. And then for the second term, we are going to use the chain rule. We are going to use the multivariable chain rule. Right? So we can write this by dt as dxi dt times the partial derivative of e with respect to the coordinate xi. Okay, where here we have a sum. Should not use I. I'm just going to use another letter. To use J. Okay. Where here is a sum from J equals to 1 to J equals to 2. Because we're doing things in 2 dimension. Note of this part over here. So this part, so notice that I have arranged it in such a way that this is equals to Vj. So here is Vj, and this part where the gamma comes in, the Christoffel symbols come in. Okay? In general, so for each I and also j, we can in general write this partial derivative in terms of superpositions of the basis vectors. Similar to what we did over here. Okay? So for each I and j, this is going to be equal to summation of superposition of the basis vectors again. Okay? And the symbol that I'm going to use is gamma. And this is where the gamma comes in. Now, because we have to take care of this one for each I and j, we have to also keep track of our i's and also our j. So at this gamma, we have to also know what is the I and j that we are concerned with. When now we have a summation k equal from 1 to, in this case, 2 again. Okay. So this is starting to look at the geodesic equation. So now I'm going to rewrite this on the next slide. So the first term is just this one. I'm going to change the index, the letter of the index a little bit. I continue over here. What I have is dvk dt dk. So here I'm just changing my dummy indices. Just changing my dummy indices. And for the second part, notice that we now have how many sums? We have 3 sums that we have to take care of. One is this first sum, right, with respect to I. Then the second sum with respect to j. The third sum with respect to this k. Okay. So I'm just going to combine them together to be summation of I, j, and k from each of those indices from 1 to 2. K, I, j, vi coming from this. Then we have vj, and then we have e. And the reason why I changed the dummy index, the dummy indices in the first term is because so that now the basis vectors are labeled by the letter k. So what I can do now is that I can just take it outside the summation involving k. Right? And inside we are left only with the summation involving I and also j. Right? And if we now require this to be equals to 0, this implies that each coefficient of ek must be equals to 0. Right? The only way for a vector to be equals to 0 if each component vanishes. Right? So that is the only way for a vector to be equals to 0. Right? This you can see is indeed a vector because we have a superposition of some multiples of the basis vector. And so yeah, so requiring that dv by dt vanishes, that implies that each component vanishes. Okay. If you look at this one, right, you should then recall. So in order to proceed, you should recall that vk by definition in our construction is equals to derivative of the coordinate with respect to time. And so we obtain this equation, which is the geodesic equation. All right. Is that okay? Here, I am motivating the form of the geodesic equation only using flat spacetime. As it turns out, when you go to considering curved spacetime, the same equation appears again in order for you to describe straight lines. Of course, the more technical construction is going to be a bit more detailed, and you need to be a bit more careful. But the end product is still the same equation. This geodesic equation. So now, how do we relate this to the idea of gravity? Recall that I said just now that I said at the beginning, where I recall what we learned yesterday, that if gravity is seen to be as a fictitious force, then freely flowing particles must actually be moving in straight lines, right? Then what are those straight lines? What are those straight lines from the perspective of an accelerated frame of reference? How would we describe straight lines in the frame of reference and in an accelerated frame of reference? We need to describe straight lines using the geodesic equation. Using the geodesic equation. So that was actually one of the origin that led Einstein to consider curved spacetime. Okay. To consider curved spacetime in order to incorporate gravity, to include gravity in the study of relativity. Okay, this part, okay. I know that I did not really show the geodesic equation in the context of curved spacetime, but if we are to talk about straight lines in curved spacetime, we really need some extra input as well. Before we can talk about the geodesic equation, we need to first talk about the notion of parallel transport, right? So what do we mean by moving vectors, uh, parallelly in curved spacetime? We need to talk about that one first, and then only we can talk about what do you mean by straight lines. Straight lines are passed in such a way that the tangent vector is proportional to the tangent vector. The rate of change of the tangent vector is proportional to the tangent vector itself. Or more restrictively, straight lines are passed in such a way that the rate of change of the tangent vector is equals to 0, right? So it is from that second definition that I said just now is what led to this geodesic equation. Yeah, so just now I said, we need to talk about what do you mean by parallel transport, right? And in order to talk about parallel transport, we need to talk about covariant derivative. Then only once we talk about covariant derivative, then only we can talk about geodesics. All right. So I hope that this gives a little bit of motivation why the geodesic equation looks like it looks here. So towards the end, I will give you. I'm just going to link for you to refer to if you want to learn more about parallel transport, etc. Parallel transport, covariant derivatives, etc. Okay, any question about this? Okay, no question. I touch it. The next thing. So this is not part of the original outline, but I thought that maybe I should probably talk about this part a little bit. Right, so we've been talking about I've been talking about how we can the idea of GR is to incorporate gravity as of a curved space-time, right? But one of the things that GR must reproduce is it must be able to reproduce the standard Newtonian gravity in some certain limit. In some certain situation, it must be able to reproduce Newtonian physics. Otherwise, the new theory is not going to be a valid theory, because it cannot incorporate what we know is already right in some situation. The Newtonian limit is still valid whenever we have a weak gravitational field. That is, for example, when we're describing things on the Earth, then definitely the Newtonian physics works. Newtonian physics work. So we're going to look a little bit about the so-called Newtonian limit. Okay, so to talk about Newtonian limit, we need to talk about first talk about what are the equations describing Newtonian physics? All right. So there are two equations that describe that describe gravity in Newtonian physics. One is this Poisson equation for gravity, which describes how objects with mass are the sources of gravity, or how objects with mass generates gravity. Where this rho over here, the next one, I don't have to write down. So we have this first equation, and the second equation is Newton's second law, which describes how objects with mass are affected by gravity. Right? So in this notation over here, what I've written over here, this phi over here is the gravitational potential energy for a unit mass that is generated by objects with density rho at the same point. So in GR, these two equations are going to be replaced by, the first one is going to be replaced by the Einstein equation. First one is going to be replaced by the Einstein equation. This one is going to be replaced by the Einstein equation. And this second one is going to be replaced by the geodesic equation. Right? Because recall that, because take note that this one is describing the motion of object affected only by gravity. So in GR, this means that this is the equation that correspond to objects that are not affected by anything else other than that is not affected by anything else, that is not accelerating or anything. Okay, so a bit of comment about the gravitational potential energy. If you recall in mechanics, you would have learned that we can associate gravity with what's known as the gravitational potential energy. We often use the letter U to indicate the gravitational potential energy. And we know that the gravitational potential energy outside the Earth is given by this Gm over R. But notice that we do not say anything about the potential energy inside the Earth. We do not say anything about the potential energy inside the Earth. Now, the phi is defined to be the gravitational potential energy per unit mass. So this phi is U over the small n. Right? If we then proceed to consider the gravitational force somewhere even within the Earth, even within the Earth, that's where we are going to be led to this Poisson equation. Okay? In this region, the potential in this region is described by this so-called Laplace equation, because we have only a vacuum outside the Earth, right? So that the matter density in this region is equal to 0. Right? Whereas inside the Earth, the density rho is not going to be equal to 0. So inside here, we need to solve this equation. Oh, is it again? In order to find what is the gravitational potential inside the Earth. right? Okay, the Newtonian limit. We define the Newtonian limit with three conditions. One is that gravity is weak. All right. The first condition is that gravity is weak. That is the first condition of the Newtonian limit. So what does this mean? This means that there exists some frame of reference, the standard coordinates e, x, y, and z, where we can write the metric as a summation between the standard Minkowski metric and some metric with very small components, right? With very small components. So this is the Minkowski metric. And this is some what we call as the some perturbation away from the flat spacetime. This means that the each component of this H over here is very small. It's less than one. The second condition is that the gravitational field is static. What this means is that there should be no t dependence in the metric. All right, so that we have that the rate of change, and we have that the derivative of the metric, the whole metric, with respect to time, with respect to t, must be equal to 0. And the third condition is that all particles are moving slowly. So these are the three conditions that define the Newtonian limit. Okay, so now I'm going to describe to you how, using these three conditions, we can reproduce the standard the Newtonian physics limit, the Newtonian gravity framework. Okay, so so suppose that we consider the path of a freely falling particle parameterized by the particle's own proper time. So recall yesterday I said that proper time is the time on the clock, the time as observed by the observer himself. By proper time is the time on the clock that is moving together with the observer, right? So from the condition of the slowly moving particle, we obtain this criteria. How do we obtain this? So slowly moving, just now I said that this means that this has this, right? Then in a case of notation, again, this is equal to di by d tau by d t. Okay? And this is equal to di dt, di tau over dt d tau. Right? If you then bring this dt d tau to the right hand side, and you obtain this equation. So this means that the rate of change of the position with respect to the proper time is very much smaller than the rate of change of the coordinate time t with respect to the proper time tau. So what this means is that when we consider the geodesic equation, this implies that we can ignore terms containing dx and d tau in the geodesic equation. This is what this condition implies. So that if you now consider the geodesic equation with all the sums just now, we are left only with the equation. Well, notice that over here I have so if you look at the geodesic equation, I have already ignored all terms containing dxi by d tau. Right? So we are left only with this part. And notice that in this equation, we only need to consider the 0, component of the Christoffel symbol. We need to only consider the 0, component of the Christoffel symbol. The next thing that we're going to look at, if you refer to the equation that defines the Christoffel symbol, if you consider the 0, component, this is what we have. Right? Where here I have used the Einstein summation convention. Right? So take note of this. Lambda, 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 lambda. I should really have a summation of lambda from 0 to 3. Now, from the condition that gravitational field is static just now, is the derivative with respect to time to 0. By the way, so this one, recall that d is equal to d by d. So from that condition, this term equals to 0, and this term equals to 0 as well. So we are left only with this last one, and only with this. I want to say one term, but it's actually 4 terms because we have a sum. So remember that we have a sum here. We have a sum there. Okay, so now we have used 2 of the 3 conditions. Right? We have used 2 of the 3 conditions: the slowly moving particles condition and also the static gravitational field condition. Now we're going to use the plus condition. All right. Okay. Last condition, which are we can write the metric of the spacetime in this coordinate in this particular way with this condition. So just now I talked about the inverse metric. Why do I talk about that one? Because here we're also going to use again the idea of the inverse metric. Right? So from the definition of the inverse metric, it follows that inverse metric G is going to be equal to the sum, or the difference between the inverse metric of the Minkowski metric and also the inverse metric of this H. Right? Let me also, perhaps I should recall this part so that you remember. So the Minkowski metric, in our notation, it is equal to -1 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. This is the Minkowski metric. And the inverse metric is going to, so for the Minkowski metric, the inverse metric is going to take the same form. So the inverse metric is also going to be, use this diagonal minus 1, 1, 1, 1 as well. Okay, so how do we use that condition, the first condition that I mentioned just now? Because the components of this h over here is very, very small, and this implies that we can ignore terms containing higher powers of h, right? Which means that we can ignore, for example, just write it this way. We can ignore terms containing products of h. Right? Suppose that you have h00 times h00, you can ignore that. h01 times h00, you can ignore that. So every product of h, every product of components of h, you can ignore it. Right? So that we need to only take care of, we need to only keep track of terms containing just a single h, just a single h, without any products with itself. If you refer back, if you now substitute this condition, what we have here, into our Christoffel symbol. So this was our Christoffel symbol just now. Then we substitute our inverse metric here, and this is our metric, right? Then notice that we are left only with this term. So because so firstly, this one is just a constant, right? So that the derivative of a constant is just going to be 0. So this one is already vanished. That would already vanish. So we are left actually with focus on this part. We are left only with this one times. Okay. There is a typo. This one should be lambda. Okay. We are left only with this one, and then minus h mu lambda times the rate of change of h00. Right? But notice that this term we have a product of h. We have a product of h, so we can ignore this. So this one is approximately 0. So we can ignore that one. So that we are left only with this term. Where again, recall that we are using the Einstein summation convention to have this sum. So we can substitute that into the geodesic equation. Obtain this one, to obtain this. And once we have this, then only we need to we have to analyze. So remember that this is actually a set of equations, one for each mu. This is not a single equation. We have a set of equations over here. That one for each mu. So for mu equals to 0, we have from the condition of a static gravitational field, we have that for mu equals to 0, this equation is the condition that this is equal to 0, so that the rate of change of the coordinate time and dt by d tau is constant. Is equals to constant. This is what the first the mu equals to 0 equation gives. What we're more interested in is the equations and when mu is equal to 1, 2, and so 3, right? Which would keep track of the position in space of the particle. So for the spatial part, if we substitute in this, we get this equation over here. Where now to proceed to this part over here, recall that this one minus 1, 1, 1, 1. So we have a summation here from 0 to 3, and where our I for each I equals to 1, 2, 3. Okay, we have this equation, right? And so notice that eta I mu is going to be equals to 0 always, unless lambda is equal to I. It's only when lambda equals to I that eta is going to be equals to 1. And so we are reduced to this equation. Over here. So equal to 0 for lambda not equal to I, and equals to 1 for lambda equals to I. Now we no longer have any summation to do. So we are left only with this equation. Then what we can do next is that we can divide both sides by dt by d tau square. So the effect on the left hand side is that we are going to turn this second derivative of xi with respect to tau. We're going to turn it into the second derivative of xi with respect to time. And okay, so at this point you can start comparing this equation with the Newtonian equation. Okay, so if you now compare what we have over here with the Newton's second law equation, right? Then notice that in order for us to have the Newtonian physics, we must have that h naught must be equals to minus 2 times 5. Okay, 2 times 5. So it follows that the appropriate metric described in Newtonian physics is one where g naught is equals to minus 1 minus 2 pi. Where I recall that g naught is equal to eta naught plus h naught, and this is equal to minus 1 and this is equal to minus 2 pi. Okay. So from this example, we can see how the how the curved space-time framework can indeed incorporate Newtonian gravity. It can indeed incorporate the Newtonian framework in, in this new theory, in GR, given some appropriate limit. Okay, question. Perhaps we should take a quick break for a while, digest the information. All right, so this part, do you have anything that you want to ask? Okay, can you guys still follow what I'm doing here? Okay, very good. All right, let's just take one minute break and then we continue. So now let's continue to the next part, all right? So what have we looked at today? So we have looked at the idea of the geodesic equation, and I have described to you how we can rederive, how can we reproduce the Newtonian physics using the curved space-time framework, right? And one thing that I wanted you to take note is that notice that the metric is proportional to the um, uh, gravitational potential, right? So the metric is proportional to the gravitational potential in the Newtonian limit. Oh, and another thing, notice that the Newtonian limits only restrict what the form of the 0, 0 component of the metric. It doesn't say anything about other components of the metric, right? It doesn't say anything about other components. So the next thing that we're going to look at is we're going to briefly look at the Einstein equation. We're going to look briefly at the Einstein equation. So now, just now I mentioned to you that in Newtonian gravity, we have two equations, right? One is Newton's first law, which we have already which I've already said that is going to be replaced by the geodesic equation, and we have already looked at the geodesic equation just earlier. And I said that the geodesic equation describes what is the straight lines in curved spacetime, referring to the natural pathways and natural paths that anything that is not affected by anything else other than gravity is going to take. So the Einstein equation is the equation that is going to replace this Poisson equation. Okay. Where just now recall that I said that this equation is the equation that describes how massive particle, how particles or the objects with mass generates gravity. Right. Just by looking at this equation, uh, just by looking at this equation, we can see that if we are to generalize this equation, to something in terms of objects in curved spacetime, we can see that from the left hand side we have second derivatives of the gravitational potential. We have the second derivative of the gravitational potential. So we can guess that if we are to describe gravity with curved spacetime, we should replace this left hand side with something involving the second derivative of the metric. Meanwhile, the right hand side, we have density over here. So it must be replaced by something that characterizes the content of matter. It must be replaced by something that characterizes the content of matter. So schematically, we should have something like this. Right? We should have our new equation describing gravity, describing how gravity is produced, must be something like this. It must be on the left hand side we have the second derivative of the metric, and the right hand side we have something that describes the matter content. Okay. Okay, so this part is perhaps going to be a little bit superficial because we have not done any proper tensor calculus, right? So it is going to be a little bit just an overview. Okay, so if you recall, when I was talking about curvature before, I said that there is indeed a better way for us to describe curvature, right? And that is using the Riemann curvature tensor, what is known as the Riemann curvature tensor. And this is what the Riemann curvature tensor looks like. Okay? It has four indices. Which means that if you are to represent it as a metric, in for a four-dimensional spacetime, it is going to be a 4 by 4 by 4 by 4 matrix. Right? So yeah, and it is given by derivatives of the Christoffel symbol. It's given by derivative of the Christoffel symbol as well as products of the Christoffel symbol, right? As well as products of the Christoffel symbol. Okay, but recall that this Christoffel symbol, on the other hand, involves derivatives of the metric, right? So our first idea might be that we want to use this Riemann curvature tensor to replace the um, left hand side, right? But then we cannot do so because for the reasons that I'm going to why? Because after this we're going to look at what is a suitable thing to describe the right hand side. Right hand side is going to have only two indices. It is going to have only two indices, but the Riemann curvature tensor consists of four indices. So we cannot use this one. We cannot use the Riemann curvature tensor. Instead, there is another quantity that we can construct from the Riemann curvature tensor, known as the Ricci tensor, which is defined as the summation of some components of the Riemann curvature tensor, which is in this way. Okay. So our first guess then would be to replace the left hand side with this Ricci tensor. Meanwhile, so this one is for the left hand side. Meanwhile, for the right hand side, we do indeed have something that could characterize the matter content of a continuum, right? of a body of matter, right? Which is known and that is the energy momentum tensor or the stress energy tensor. Okay? So by definition, the energy momentum tensor or the stress energy tensor, which we denote by this letter T, right, with two upper indices, mu and nu, by definition, it is the flux of the four momentum density across a surface of constant x mu. And this is how it is defined. Now, for a body of matter, let's say we have a fluid, for example, and the physical meaning of each component of this tensor schematically is given this way. Schematically, the time component or the 0, 0 component is the energy or the mass density. Because I recall that in relativity, energy and mass are just the same thing. The time space component is the T0I, describes the energy flux. The space-time component Ti0, it describes the momentum density. Whereas this one, the space component, describes what is known as the stress. So, given this, we would then guess that we should replace the right hand side with this stress energy tensor, right? But we need to first do something with it in order for us to lower the indices, in order to match the lower indices in the Ricci tensor. And for this one, we can do that by define another quantity using the metric tensor. So this is something you will learn if we actually go through tensor calculus. Right? So this is not something so this is something that we can do in the tensor calculus. So, but here I'm just going to state this fact over here. But what I want to focus next is that I want to motivate you why the stress energy tensor describe all of these things. Why the stress energy tensor describe the energy, why the 0, 0 component describe the energy or the mass density, and this component describes the energy flux. This component describes the momentum density, right? And I'm going to use this definition. Yeah, so remember this definition. So the tensor component is the flux of the momentum density, of the fall momentum density across a surface of constant x nu. So let us consider a collection of particles that is dense enough that we can regard it as a continuum. Like, for example, a body of water, for example, or whatever fluid that you want to consider. So we could then characterize the fluid with quantities such as the density, the pressure, the viscosity, etc. Because I want to illustrate to you how we can interpret components of the energy momentum tensor as the energy density, momentum density, etc. Let's consider a 2+1 dimensional spacetime. What I mean with this is that let's consider a spacetime with 2 spatial dimension and 1 time dimension. Okay. So that we can draw space-time diagram in this way. So this is y, x, and we consider a body of matter, a fluid, right? It's dense enough so that we have particles everywhere. That form the fluid, all right? And then we're going to analyze the source energy tensor using the definition. Start by considering the T mu 0 component first, right? Which by definition is the flux of the momentum density, momentum P mu density across a surface of constant x naught, right? Which means that across a surface of constant P. Now, how can we find the flux of momentum density across the surface? One way that we can do that is that, so we have just now the space-time. What we can do is that we can consider surface of constant. We can consider a surface of constant T. So this is a surface of constant T. And the flux means that we need to find out what is the momentum density on this surface, right? And now I would like you to recall that the component of the momentum is, the first component is the energy, the second component is the momentum in the x direction, and the component is the momentum in the y direction. Then, by definition, if we consider any point on this surface, so let's say this point over here, then the 0, 0 component of the momentum tensor is, by definition, is the energy within this infinitesimal area. So this is delta x, this is delta y. Energy within this area in the limit as the area goes to 0, right? So that by definition T00 is the momentum density on this surface. That is the flux of the momentum density across this constant surface T. So by definition, T naught naught is given by this limit. And this is none other than the density of the fluid at any particular time. The density of the fluid at any, or rather on the density of the fluid at this time T. At time. So again, recall that so this one is in relativity. This is equivalent to mass. So if we take mass and we divide it with the area, and we take the limit as the area goes to 0, we get the density. We get the mass density of the body of water, for example. Okay. While the 1,0 component, by definition, it is given by this. All right, it's going to be given by this, and this in the limit as the area goes to 0 is going to give you the momentum density. Same thing goes to T to 0 component. You're going to get the momentum density in the y direction. So, and hence the if we look at the first column, we get that the topmost component is the mass density or the energy density, and the other two components are the momentum density. Right? Now we can do the same thing with the E mu 1 component. All right, but this time, so if we consider again, this time instead of a constant T, we need to consider a constant X. So let's say if we consider this surface over here, we can consider this surface over here, and we can consider this point, for example. So this is our delta T, this is our delta, this length, this length. Okay, and we consider this point. And our T01 is, by definition, the energy divided by delta T divided by delta Y. Right? And take the limit, and as we take the limit as delta T and delta Y goes to 0, what we get is that this is the flux of energy that passes through this surface at this point. We look at the T11 component, get this expression where notice that this is just the force. This is just the component of a force in the x direction. Right? And force over, in this case, over the length, this is going to give you the force per unit length, which is just the pressure. Lastly, we have this one, y component of force per unit length. This is the shear into +1 dimension. In 3 + 1, this is going to be per unit area. In 3 + 1 dimension, this is going to be per unit area. But we're just considering a 2 + 1 space-time, so we have per unit length. And that this is how you can intuitively think of why the components of the stress energy tensor has the interpretation that they have. Okay. Okay, any question? All right, take it as no question. Then let me just proceed then. Okay, so then our first guess would be that we should replace the Poisson equation with something like this. And that is the Ricci tensor is proportional to the stress and J tensor in this way. However, we have a bit of a problem if we use this equation to replace the Poisson equation. That is because if we then consider local conservation of energy momentum tensor, which require this quantity to be true, where, so this is something that I did not introduce in this workshop. This quantity over here is what is known as the covariant derivative. Right? So, so the covariant derivative of the stress and energy must be true. But however, if we then proceed to consider the covariant derivative of the Ricci tensor, it is not equal to 0. Instead, it is given by this quantity. The R is yet another quantity that I did not introduce. So this is the summation of R mu mu. Sorry, R mu mu. So yeah, so there's quite a number of things that I did not introduce that we have not looked at properly in order to derive the Einstein equation. But yeah, I'm just going to mention it. Okay, so in general, so we face with this problem over here. On the left hand side, we always have this one, but on the right hand side, we don't have this. We don't have that the right hand side. We don't have that the left hand side always vanishes. And that is indeed a problem. Nevertheless, you can notice that if we do a bit of algebra, a bit of rearrangement, we can write. So from this results over here, we can bring the right hand side to the left hand side to obtain this quantity. Notice this one over here. So what we can do is that we can define a new entity that always satisfy this condition. So this quantity is what is known as the Einstein tensor. What is known as the Einstein tensor. And the next best thing then, perhaps it is not. So perhaps the left hand side should not be the Ricci tensor. Instead, it should be the Einstein tensor, which is indeed what the equation for GR. It is from here that we arrive at the Einstein equation. So, and hence we arrive at the Einstein equation here. Okay, so as I said, so this part is going to be a little bit superficial because there are there's quite a number of things that we did not look at properly. But yeah, this is how you can arrive at the Einstein equation. Yeah. Perhaps I'd like to say that ultimately the appropriate equation of motion really is postulated, right? So like what we did over here, we begin with the Poisson equation, right? And then how would you get the new equation? You get it by guessing, not just simply guess. You have to have reasons why you guess it that way. Like just now, the right hand side, we have to replace it something that contains the density as well, something that contains the mass density. And indeed, even in special relativity, we have that stress energy tensor. So we know that we can replace it with that, right? Meanwhile, the left hand side, we start by guessing that perhaps we can use the Riemann curvature tensor. No, because we have a problem, because the indices on the left hand side and the right hand side would not match, right? For equations involving tensors, the uh, the indices must match on the left and on the right hand side. So the next best thing would be to try the Ricci tensor. If we do that, we have a problem. We face with an inconsistency. Okay? Then by try and error, or rather by observation, we arrive at this entity known as the Einstein tensor. This is proposed as the new equation that should replace the Poisson equation, and it works, right? And it works. It can describe what happened in the real world, and so far it works. Okay. Any question? So we have arrived towards our last part of the workshop, and the last part. So this last part is not going to involve anything about the geodesic equation or the Einstein equation. So this last part is pretty much independent from from this topic about the geodesic and the Einstein equation. You need to know about what you need to remember in order for us to talk about the last part is just the fact that light cones, or the path of light, is described by vanishing metric. It's described by ds squared equals to 0. Okay, but before we go to that one, any question? All right, if there is no question, let's just proceed to the last part then. Okay, so this last part where we are going to try to draw the light cones in this curved space-time. So we are going to begin with the Schwarzschild black hole. Okay, but before that, let's begin with a bit of recap, or rather, let's just look at the Minkowski spacetime first. Right. So recall that I mentioned yesterday that the metric for the Minkowski spacetime, the metric for a 4-dimensional Minkowski spacetime, that is 3 space and 1 time, is given by this metric in the convention where c equals to 1. Now for the spatial part, we can use the spherical polar coordinates for the spatial sector to write it in this way. And now let's consider the path of light, the path taken by lights traveling in the radial direction only, in the radial direction, so that so that there is no change in the theta and phi direction. So if we are if you imagine so this is z, this is y, this is x, and this is a sphere. Can imagine that we are considering light that is traveling just in this direction, for example, in along the radial direction, without changing uh, the angles. It can be in this direction or this direction or this direction or this direction. In any radial direction. Then in this case, on one hand we have that. And in this case, first we have that d theta and d phi must be equal to 0 because there is no change in the angles. So this part vanishes, this part vanishes. Then recall that the path of light, so the path taken by light, right? So recall that this means that ds equals to 0. So we are left only with this equation that characterizes the path of light. All right, and we can manipulate this equation to obtain this differential equation. That is dt by dr equals to plus or minus 1. Plus or minus 1. What does the space-time diagram looks like? So now because there is only change in the r coordinate, we need not concern ourselves with the theta and also the phi, the theta and the phi coordinates, theta and phi direction. Right? So our space-time diagram, we are going to focus on evolution of the position of the coordinate r of the light as time goes on, as time increases. So if we consider a light that begins at the center, the only way is that it can only move outwards. It can only move outwards. So that time that the light will be traveling in this direction. Okay? Would be so the light will be traveling in the increasing r direction. If we consider a light that begins at some other point, r is not equals to 0, and it can either increase in r corresponding to dt by dr equals to 1, or it can travel in the opposite direction towards a decreasing r corresponding to dt by dr equals to -1. This form the light cone, or to be more specific, this is the future light cone. It is future directing light cone in the Minkowski space in polar coordinates. If we take the direction of time to be the opposite direction, of course we are going to get this and also this. All right. Okay, so this one I hope is clear because we are going to use this one. Right? We are going to use this diagrammatic representation to study to study the behavior of light in the black hole metric, right? So in particular, we're going to study the behavior of light. We're going to look at the behavior of light uh, as it moves through space-time describe as it moves through the space-time outside a black hole. Okay? So this one is clear. If any question about this one? Right. Okay. Thank you. Okay. Another quick note. We can also define what's known as the light cone coordinates. Okay. Because if you look at this one, right? If you look at this this equation, you would notice that this, for example, this line is just a straight line, right? It is a line described by t minus it is described by t equals to r and then plus some constant So in other words, this line is described by t minus r equals to constant. Meanwhile, alright, I now consider another part of light, and for example, this one here. This is going to be described by, use another color, slightly different color. Okay, so this is going to be described by yet another t plus r equals to constant. Right? But a different constant than the previous constant. So this is going to be a I don't know, u2, for example. And u equals to maybe this one is minus 2, I don't know, something like that. Okay, so this is going to be a constant equals to minus 2, for example. So, and then the previous one might be constant equals to minus 3, for example. Okay, so meanwhile, this one, the green one, is going to be described by t equals to minus r plus constant. So in other words, this straight line is going to be described by t plus r equal to a constant. But this constant is this point intercept over here. So maybe 5, I don't know, it should be 3. Okay, 3, this is 3. Alright, and I can consider also another path followed by line. So this is going to be yet another t plus r equals to constant. So this is going to be probably 4. So what we can do is that we can now use this path of light to define a new coordinate system. We can define this path of light to define a new coordinate system. Just as in our standard coordinate system, T and R, we have surfaces of constant T. So this is constant T. So this one, these are constant T. These are constant R. And we have used constant t and constant r as our coordinates. Okay. What we can do is that we can use another coordinate that is adapted to the path taken by light. Okay. That is constant t minus r and also constant t plus r. Okay. And typically we would denote the coordinates with this letter u and also v. Right? So we define these new coordinates u and also v via this relation where u constant follow the path of light in the increasing r direction. Right? So this is what we call as the outgoing light. Outgoing light. Okay. Because if you imagine, okay, if you go back to this one, that path of light, suppose that so this path of light, it is going to move in the increasing r, which means that it's going to move in this direction, going away from the origin. Whereas the light that is described by constant v going to correspond to what is known as the ingoing light, because it is moving towards center, towards r equals to 0. Now we can do the manipulation similar to what we did before this, when we were changing the coordinate from the Cartesian coordinate to the plane polar coordinates. We can do a similar manipulation to write the metric in a new coordinate system, in this u, v, theta, and phi coordinate system. So this would be an exercise that you would want to do. Try to do this one. You can begin with this coordinate system t, r, theta, and phi. Right? So try to change the coordinate system to show that in this new coordinate system, now the metric looks like this. Where this r over here must be implicitly defined in terms of u and also v. So I still leave it as r, but really we should understand that this is r as a function of u and also v. R as a function of u and v. To be more precise, this is actually what do we have here? So if we subtract v minus u is going to give us 2r. 12 divide this by 2. Okay, so this is our r in this new coordinate. Okay, why do I introduce this one? Because the next thing is that we're going to look at black holes. I'm going to begin with this a little bit misleading, actually, a little bit misleading analogy, but nevertheless. So suppose that we consider an object of mass m, right? So right now think about Newtonian physics. So suppose that we have an object of mass m, right? That we project vertically upward towards the sky. Okay, an initial mass vi. The initial mass of vi. So this is perhaps something that you have encountered in mechanics. Okay? Then the escape velocity, which is defined to be the minimum initial speed at the mass need to have in order to escape to infinity, right? That is from this picture. In order to escape to somewhere very far away from the Earth, the escape velocity is given by this formula. Notice that how the escape velocity depends on the mass of the Earth and also the radius of the Earth. Okay? Now, for a certain combination of mass and radius of maybe a planet or a star, right? You could have a planet or a star where the escape velocity is equals to c. Now, does this mean nothing can escape from this star? Any idea? Suppose that we have if we have something, or if we have an object of mass m and vh in such a way that the radius of that object is given by this formula, then the escape velocity for that planet or star is going to be equals to c, right? So does this mean that nothing can escape the star? Well, if you think it carefully, then this is not really the case, right? Because here, notice that the escape velocity is the minimum initial speed, right? And notice that by definition, how we find this in order for us to find the escape velocity, we assume that the velocity of the we assume that the final velocity of the object of this mass m is equal to 0, right? Which means that and we assume that this object does not accelerate the upward direction. The only acceleration is due to gravity, is due to the gravitational force. Right? So there is nothing actually stopping us from considering something that can accelerate upwards, right? So no, this is not really a black hole, because there is a crucial difference between a black hole and this situation. So this one is just about the escape velocity. It's just about the initial speed or the initial velocity. Whereas, so that if let's say we consider something that accelerates, let's say something in a rocket or something, then that thing could still escape. Crucial difference is that with a black hole in GR, nothing can escape, even if that thing accelerates very hard, right? It wouldn't be able to escape. We'll see why in a moment. So, I will introduce to you the metric that is describing the black hole, right? The simplest black hole. It's known as the Schwarzschild metric. Right? So this metric is actually okay. It is actually a metric describe the space-time outside of any spherically symmetric body, including the Earth, provided that the outside is a vacuum. So suppose that we are studying in GR and we consider the Earth. So of course we have Earth. Then the metric outside the Earth is precisely given by this metric in the spherical coordinates. This same metric. And the parameter m, okay, and the parameter m is the mass of the spherically symmetric body that we can identify. We can identify this parameter m to be the mass of the spherically symmetric body. Something that you would notice immediately, just by looking at the form of this metric, you can notice two things. One, that the metric diverges as r goes to 0. What I mean by this is that the component of the metric blows up as r goes to 0. So notice this part over here. This part over here. So as r goes to 0, this term is going to go to infinity. So that as r goes to 0, we have a problem over here. We would have an infinity as r approaches 0. Okay. Meanwhile, this term, this that we have we have this power to the power of -1 here. This term would go to infinity as r approaches this special value. R equals to 2dn. And another feature that you would notice is that the metric approaches the Minkowski metric as r goes to infinity. So as you take r goes to infinity, this term is going to vanish, this term is going to vanish, and you are left only with a metric that looks like the Minkowski metric. So this means that the coordinates adapted to someone at infinity, someone that is far away from r equals to 0. Right? That this t is going to denote the time as measured by someone at infinity, someone far away from r equals to 0 or any other r. Okay. So the significance of this one in particular, we're going to look at in a moment. The significance of r equals to 2gn. Okay? All right. So this is what is known as the we can identify this as sort of the size of the black hole. Okay. Now what I want to do is that I want to consider the path of light that is traveling again in the radial direction. That's something similar to what we did just now in the Minkowski spacetime. We consider the path of light the path taken by light traveling in the radial direction, such a way that there is no change in the theta and also phi coordinates. Right? So we see that the path of light must satisfy this equation, right? This equation. So this equation over here. Okay. So we compare it again. This equation, if we set this one goes to 0 and this one goes to 0, this term is going to vanish. And for lights, ds square must be 0. So we are left only with this term, which we can rearrange to get the path of light must satisfy this equation. That is dt by dr equals to plus or minus this quantity. which I can write as 1 over 1 minus 2 gm over r. Okay. Something that you will notice is that dr by dt approaches plus or minus 1 as r goes to infinity, and it approaches plus or minus infinity as r goes to 2 gm. So with this, we can try to draw what is the shape of the light cones, what is the shape of the path of light in these coordinates. Okay. Let's try to draw that. And begin by, so we have our t coordinate and our r coordinate. And let me denote this special position. R equals to 2 gm. Okay. And let us consider, let's say, the path of light. Let's first consider the outgoing path, the outgoing light first. That is the path with positive direction. So so the plus correspond to outgoing, and the minus correspond to the ingoing light. And if we try to draw the path of light, consider then somewhere here, the path of light is going to look something like this. The outgoing light is going to follow this path, right? Then as we go closer and closer towards this r equals to 2 gm, notice that the gradient is going to approach past infinity, which means that we are going to have even steeper path. And then as we move closer, we have something like this. Right? If I now try to draw the ingoing light corresponding to the minus sign, we're going to have something like this. All right. Okay. And this diagram can also be used to represent like so this is what happening within the same amount of time. Right? So within the same amount of time, some delta t, for example, if the light starts traveling, if let's say the lights start traveling from here, then it would cover this much distance. Whereas for a light that is starting from here, it's only to cover this much distance. So for the path of light that starts here, is going to cover this much distance, and for light starting here is going to only cover this much distance. All right. So some observations that you can see from here. The light cones are closing up as R approaches this special point. This is very different from the Minkowski spacetime now, where we see that the light cone is always at 45 degrees. It is always at 45 degrees everywhere for all R. And Secondly, notice that the outgoing light takes longer to get away from near r equals to 2 gm, as I said just now. So if the light starts from this point, then within the same amount of delta t, it can only travel this much compared to a light that starts from this point. It can only travel, it can travel a much further distance, right? So, and the third one, this one, in falling light, never reach r equals to gm, r equals to 2 gm. So this is something weird. This is something weird. Okay. So let me begin with this one first. The second one first. So this is what this is as best as we can say about thinking of the gravity of the black hole is sort of pulling light into the black hole. But even though that statement is not actually accurate, because the black hole doesn't suck anything, just as the sun doesn't really suck you into the sun, right? So the black hole doesn't do that as well. And this one is actually something weird. So this is the weird D, right? The infalling light never reach r equals to 2 gm. But this one is not really a problem if you study, if you analyze this thing in a bit more detail. This is not really a problem because this is really just because you are using a coordinate system that is not suitable. Purely coordinate. Because what really happens here is that the proper time of the infalling observer gets stretched out, right? So this one I'm going to gloss over, and I'm not going to focus on this part. Right. So now we can see something odd with using this coordinate system, right? We would like to consider. We would like to find. Because okay, so over here you can see that this one is suggesting. So this diagram is suggesting that as if. So recall I said that anything with mass can only travel within the light cone, right? So which means that something with mass must be traveling within this one, within this, or if it passes through this, it must be traveling this, or something like this, right? And this last one is a bit odd because it suggests that since even infalling light doesn't approach, cannot cross this surface, this would suggest that nothing can even enter this surface. But that is not actually accurate because because this one is actually just a purely coordinate artifact because we are using a coordinate that is not suitable, and that's not suitable. So what we want to find next is that we want to consider, we want to find another coordinate system where we'll see that infalling light can indeed crosses this surface. So we start by first finding a coordinate system where the light cones are 45 degrees. are at 45 degree, right? So what we can do is that, so recall that for a radial traveling light, it satisfies this equation, right? So just now, the defining equation, this one here, this one here. Okay. What I can do is that we can define a new coordinate system, which would often be denoted by R star, okay, by letting d R star square to be equal to everything on the right hand side. If we take the square root of on both sides, we're going to get this equation. So before we proceed, so let me just note. So from this one, it would imply that dt equals to dr squared. Right, so light cones are at 45 degree in this dr star coordinate system. So this COORDS is a shorthand for coordinates. So next, in going to first line to the second line, I have implicitly required that R increases, R star increases as R increases, which is why I'm ignoring the other negative sign. Now, given this equation, you can solve it. You can solve it. Okay, this is another thing that you can try. So solve this one. You will find that R star in terms of R is given by this equation. R in terms of is given by this equation, and the Schwarzschild metric now reads this one. Now it now takes this form. So now one thing that you so what's the next? Okay, so let me just focus on this one first. Okay, as I said, in this metric, then in this coordinate system, light cones are at 45 degree. So that if I now draw the space-time diagram, now draw the space-time diagram. I should comment on that. So if you look at this equation, right, the range of this equation is as follows. So in our standard polar coordinates, R ranges from 0 to infinity. R ranges from 0 to infinity. Now, in this so-called tortoise coordinate, in this R star coordinate, so this coordinate R star, it cannot cover all R. It cannot cover all R. It can only cover R from 2gm infinity. And this correspond to R star from minus infinity to infinity. Okay, given this, we can then try to draw the electron. The outgoing, right, is going to be at 45 degree. To the right, and the ingoing is going to be 45 degree in the towards the left. And this is my T and this is my R star. Okay, but now we have a problem, right? Because what we did is really we are just pushing away that problematic surface R equals to G, R equals to 2gm to R star minus infinity. Right? So in other words, what we really have over here is just we have R approaches 2gm as R star approaches minus infinity to the left. So we don't want to do this, right? That's not the point of us changing the coordinates, right? Because what we want to study really is what is happening at that special here surface R equals to 2gm. So the next step would be, now I introduce to you the background coordinates, right? Background coordinates. So what we can do next is that we can define the tortoise background coordinates in this way, right? Where now constant u now keeps track of constant u. So this one is constant u. So constant u, and this red lines constant v. So referring to this v and this u. So let's say if this one is u1, this one is going to be u2. It's larger than u1. So recall what I showed to you before this about the Minkowski spacetime. As if this one is v1, then this is v2 that is smaller than v1. Right? The more important point is that these are lines of constant u. Okay, so these are the lines of constant u, 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 and the red lines are lines of constant v. So the metric now looks like this in this new coordinate system. But our focus is not really about the metric anymore at the moment. We want to focus on the path of the light cone. Okay, so if we use this vu, theta, and phi coordinate, we actually still have some problem. It doesn't really solve anything yet, because as R approaches 2gm, this term would vanish. Right? So when this term vanishes, that means that the metric cannot be inverted at that 2gm point. And one of the criteria of a good coordinate system is that the metric can be inverted, right? And the metric can be inverted. So from a technical point of view, this is not quite a good coordinate system yet. But what we can do is that instead of using both u and v, we we can consider what is known as the elliptic Wittgenstein coordinates, where we just use v to replace the coordinate t. So we can use yet another set of coordinate system, v, r, theta, and phi. In this coordinate system, where you would want to recall that I said that v equals to constant follows the trajectory of radially infalling light, right? So again, we can again consider the path of radially infalling light, and we can draw the spacetime diagram using the v minus r. So if this is v and this is r, then constant v would correspond to, let's say, this line, right? So that constant v is following radially infalling light, so which means that this is the path taken by lights that is falling towards r equals to 0. Okay. Notice that now we actually no longer have that problem where the infalling light cannot cross that special surface. In fact, somewhere here is that special surface equals to 2 gm. Okay. But how can we find path of light that is traveling towards increasing r? Right, that is what we know as the outgoing light. What we know is the outgoing light. What we can do is that recall in this that take note that v is related to u in this way. The idea is okay. So v is related to u in this way. All right. See. Okay. So this one follows from. Sure. Yeah. Follow from here. Okay. So notice that r star is equals to v minus u over 2. Right? So it follows that v equals to 2 r star in terms of r plus u. So if from here I can get that this is equal to 2r plus 4 gm log of r over 2 gm minus 1. Well, you can just take this equation, this one here, you can just replace it into our formula, then plus u. And recall, then after that, recall that constant u would correspond to constant u would correspond to the path of light taken by the so-called outgoing light. So what you can do then next is that you can try to plot what is the constant u trajectory. So let's say if you choose some particular u, I don't know, maybe u equals to 10 or something, then you would get, so this one is showing you the equation of the path of light in terms as a function of v in terms of r taken by any constant u. Right? So let's say if u equals to 0, and the path of light, then the path of that line is given by v equals to 2r plus just this part. Okay? If u equals to 10, then it's going to be v equals to 2r plus this part plus 10. Okay? Something like that. If you then try to plot the graph, you would find this. I forgot to mention the thing. So you can either use this equation, or you can just set this one equals to 0 and this one equals to 0 to find that radial, to find that if you set this one, you are going to get that radially traveling light described by the following two possibilities. dVdr equals to 0, or dVdr equals to 2 times 1 over 2 gm minus 1. Okay. So this one corresponds to infalling light, and the other one must correspond to the outgoing light. Some interesting feature is that, so for R larger than 2 gm, dVdr for the outgoing light is larger than 0. Okay. But at R equals to infinity, R equals to 2 gm, dVdr is infinity. Whereas as R less than 2 gm, dVdr is less than 0. Okay. So if I now try to draw the direction of the path of light of the outgoing light, it's going to look something like this. Going to be something like, so let's see, something like this, I guess. To look something like this, something like this. And then as we approach this special surface, and at this really, and on this surface, going to travel in this direction. And then as we enter, it's going to travel in this direction. So you can see in particular, lights on this surface, light that begin on this R equals to 2 gm surface, you have two choices. I have only two choices. One, either move towards smaller r, or second, remain at r equals to 2 gm. It cannot escape to any larger r anymore. Okay, and this is the special feature of this metric over here. And this is what is known as the and horizon. This is what's known as the event horizon, because for any light that begins on this path, it can no longer escape to larger R. It can no longer escape to larger R. Right? Just now I said that this metric also describes the outer, the outside of the Earth, right? But why is it we don't face any problem? Well, the reason is because the radius of the R is larger than this 2GM. So if let's say this is the mass of the Earth, then the radius of the Earth is somewhere here. So that this section would correspond to the interior of the interior of the Earth, and that means that this section, this means that this metric can no longer be used to describe what's happening inside the Earth. So remember that I said just now that this metric would describe the outside of a spherically symmetric body, provided that the outside is a vacuum. So this metric is only valid to describe this region, but not valid to describe the interior of the Earth. So which is why the Earth doesn't have any event horizon. Right, so one last thing, I guess. I don't think I can go. We can look at the cosmology part. I just wanted to introduce this one here. So we can also introduce a new time coordinate by defining v minus r, and then v equals to constant is still going to, and then in this case v equals to constant is going to be at 45 degree in this new coordinate, right? And readily outgoing light rays is going to follow this equation for constant u. Right? Then in this new coordinate, what you're going to get is the following picture. So if I have draw it like this is our T R, this star, and this is our R, and this is our special surface. R equals to 2GM, right? Then in this coordinate system, the infalling light is still going to be at 45 degree, which means that it's going to look something like this. Okay, so this is the path of light of infalling light. So let me denote the direction. So the path of light is going to follow this. But the outgoing light is going to follow something like this. So the easiest one would be to begin with the light on the surface. It's going to stay on the surface. Okay. As a path of light that is outside is going to look something like this. Whereas inside this R equals to 2GM region, the outgoing light is still going to be decreasing in R. All right. What is the significance of this? Recall that I said that particles or objects with mass can only travel within its local light cone. It can only travel within its local light cone. So for someone at this point, it can travel this direction. For someone at this point, it can travel in this direction. It could still travel in the increasing R direction. So someone like this, someone here can still travel somewhere like this. Right? But for someone at this point, for example, he or she would have no choice but to go towards R equals to 0. By the way, I have not said anything about R equals to 0. So this R equals to 0 is really is a truly problematic point in this space-time, in this Schwarzschild space-time. It is a point where the curvature is infinity. Alright, and that's a truly singular point. What we call as a singular point in this space-time. Whereas this surface is not a true singular point; it is only a coordinate singular point. And that means that we can correct it by using a proper coordinate system. Okay? Just as the north and the north pole in the spherical in the spherical coordinates is a coordinate singular point, because at that point uh, at that point coordinate, oh sorry, not spherical, the plane polar coordinates, the origin is a singular point, in the sense that at that point we cannot we at that R equals to 0, we cannot determine what is its theta. We cannot determine what is theta in that sense. So something similar over here. This R equals to 0 is a really problematic point, because the curvature is infinite here, meaning that the gravitational pull, meaning that at this point gravity is infinite. So tidal force, for example, is going to be very huge. So you can see that from this diagram, anyone that has crosses this point would have no choice to reach R equals to 0. Okay. Right. Okay, so I don't think I have time to talk anything about the cosmology part. So just going to skip through. Just wanted to perhaps say something that. So we can also do the same thing with this metric describing the universe as a whole. And if you analyze the causal structure, if you analyze the light cones on this space-time, you would encounter what is known as the horizon problem. Right? That is, photons from the opposite direction in the cosmic microwave background would have no time to be in thermal equilibrium, yet observation shows that they are in thermal equilibrium, and that is a problem. So but in the interest of time, I'm going to skip through all of this. And yeah, and these are some references that that you can refer to if you want to study further about GR. Okay, so the first one is just actually about special relativity, and these are the common introductory texts that you can use if you want to learn GR. The one that I personally use is Carroll, right? The one by Sean Carroll. But you could also perhaps start with shoes, for example, or Hutter. Okay. And as you go further, you can start exploring the more advanced texts on GR, which are these three. Okay. So for starter, I would suggest that you begin with either of these three. So Carroll, shoes, or Hutter. So that one is textbooks. Of course, you can also refer to the internet. So this one is for cosmology. And I would like to highlight this website over here. This is a website by James Law, who was a student in USM, right? And he created this website here. Let's see if I can bring it up. It focuses more on just about learning about tensors alone, about tensors that you are that you about tensors, about the mathematics of tensors that you would need to study GR further. And in particular, he also cover the parallel transport, right? The covariant derivative, the Riemann curvature tensor, and the Ricci tensor, etc. So you might want to check this website out. There's also this project was done in collaboration between him with Dr. John and also with me as well. So do check out his website here. And you can of course also refer to other to some great YouTube videos as well. And this gives you some further references on books about GR. So you can check this out later. Okay, with that, thank you. So if you have any question, you can ask. Otherwise, that's all from me. I hope that even if you don't get everything, I hope that you still get an overview about what GR is about, and I hope that it gives you a sense of direction. Should you want to further study GR, right? So at least you kind of have a bit of some idea of what you will need to learn if you want to further study about GR later. So with that, thank you. I pass back to our MC for today.